Okay, we're going to do another example involving logarithmic differentiation here. And as we go through this example, we're going to talk about a couple of subtle little things related to finding the derivatives of logarithms or using rules of logarithms and things like that. So we've got this function here, y equals the cube root of x over x squared minus 1. We want to find derivative y primed here. So first thing we're going to do here, of course, is think of this as x over x squared minus 1, all to the 1/3, obviously. And then this is a good candidate for logarithmic differentiation. So we're going to take the ln of both sides, like this, and then we can simplify these things using the laws of logarithms. So we can get y, this is going to be 1/3, and then all in brackets here. So we bring down the 1/3 first, and then we can break up the logarithm, the log of x over x squared minus 1 into a difference of two logarithms. So this is going to be ln x minus ln x squared minus 1. Okay. Now here's where we arrive at the first problem. We have taken the ln of y, and we've taken the ln of this entire thing here. The problem here concerns of sort of what is the domain of x, or what is the domain of these expressions that we have taken the ln of. Something like x, x can be, let's say, less than 0. It could be positive, it could be negative. The same is true for x squared minus 1. X squared minus 1. Let's try and make a list here. And in fact, the same is true of y over here. Y could be positive or negative. Because if x can be positive or negative and x squared minus 1 can be positive or negative, all of these things can be less than 0, which means we have to be very careful when we take the log of them, because we can't take the log of anything that is negative. So to make sure we're not taking the log of a negative value, what we should do is when we take the log, we should make sure we're taking the log of the absolute value of these things. And that absolute value can kind of propagate through here when we break this up. Instead of taking ln of just x, we can take the ln of the absolute value of x, absolute value of x squared. Okay? Because we can think of this thing here as, if it's always going to be positive, this would be just ln of absolute value of x over the absolute value of x squared minus 1, and then we can have the 1/3 down out here like this. Okay. So we've taken the absolute value of everything, so now we know that we are not taking the ln of anything that happens to be negative. Now we get to the step where we want to take the derivatives, do implicit differentiation, take the derivative of all of these terms here. We know what the derivative of ln y is. What about the derivative of the ln of the absolute value of y? Do we have to handle this any differently now that we've taken these absolute values? So let's consider a case like this, where we've just got a simple function, y equals the ln of the absolute value of some some variable x. And we want to figure out what our derivative is going to be, y primed. Let's think of this in terms of two cases. Okay. We have the case where x is less than 0 and the case where x is greater than 0. So x can either be positive or x can be negative, or x can be positive. Okay. Now, if x is positive, then the absolute value of x is equal to x itself. And the absolute value isn't actually doing anything. Okay? Because, like, of course, when we take the absolute value of something, we're making so it's always positive. Right? If x is less than 0, so if x is negative, then the absolute value of x is actually equal to negative the value of x, right? If x is like -3, absolute value of x is 3, so negative 3 would give us that positive 3. So now let's see what happens when we can sort of rewrite our original function using each one of these these definitions for x here. So if the absolute value, first off, if x is positive, absolute value of x is equal to x, our function y equals ln x, well, sorry, ln y equals ln the absolute value of x. If the absolute value of x is just x, this just becomes y equals ln x. So our derivative is just going to be the usual 1 over x. If x is negative, absolute value of x is equal to negative x, then our function y equals ln of the absolute value of x, we can replace the absolute value of x with negative x. So this is ln of negative x. Now what happens when we take the derivative? Well, we will get 1 over negative x times -1, derivative of the inner function. So y prime is 1 over x. The negative signs cancel. So whether x is positive or negative, the derivative of the absolute value, the derivative is going to be the same. It's always going to be 1 over x. So if y prime is, if y is equal to ln of the absolute value of x, the derivative is just going to be the familiar 1 over x we had before. So now, even though we have these absolute value signs in here, inside of our lns, when we go and take the derivative of each term, it's like those absolute value signs no longer matter. So we can take the absolute value of, we can take the derivative of ln of the absolute value of y, 1 over y prime, because y is a function of x. We're going to keep our constant up front. We're going to take the derivative of each term inside here. Derivative of ln of the absolute value of x is just going to be 1 over x. Derivative of ln x squared minus 1, derivative of the absolute value of ln x squared minus 1 is going to be x squared minus 1 times 2x. And then we can say that our derivative is going to be 1/3 cross multiplied by the y, and then we're going to get 1 over x minus 2x over x squared minus 1. Just like that. And then if we want to, we can put back in what our original y function is. It was the cube root of x over x squared minus 1. This is, of course, going to be multiplied by 1 over x minus 2x over x squared minus 1. So in the learning guide or in other examples that you see in other places, when they're using logarithmic differentiation, you will see these absolute values on the arguments of the ln functions popping in, and then you might see them disappearing once they do the derivative. The whole point of this was kind of to motivate, to sort of explain a little bit why they're there and why, in some cases, you can safely remove them once you go ahead and find the derivative.